Okay, so picture this. It's 2 in the morning. Your primary application is suddenly throwing errors, so you SSH into the server to figure out what is actually going on.
Oh yeah, the classic late night fire drill. We've all been there.
Right. So you type docker run to spin up a quick diagnostic container. The terminal flashes, the container boots up perfectly, but when you try to ping your database, nothing. It just outright refuses to connect. And you're sitting there wondering, why?
Because you trusted the magic.
Exactly.
Yeah.
I mean, when we talk about modern software development, there is this almost, magical expectation of how things run. You write your code, you put it in a container, wave your terminal on, and it just works.
It's a very convincing illusion, honestly. We rely on that abstraction because it's clean and it accelerates development, but underneath that simple Docker run command is this fiercely complex system. You've got network namespaces, kernel-level routing tables, firewall rules.
Yeah, and the moment that magic breaks in production, if you don't know how it works, you're just left completely in the dark.
Which is a terrible infrastructure strategy. You really have to understand the mechanics underneath.
Which is exactly why we're pulling back the curtain today.
Yeah.
So let's unpack this. The topic of today's deep dive is Docker networking. We've synthesized 3 extensive pieces of official Docker documentation: the bridge network driver, network drivers, and the networking overview.
Right?
And our mission here is to provide you, specifically the developers and DevOps engineers listening, with a practical shortcut to being truly well-informed on container networking. We are moving entirely past that basic "it just works" phase to master the actual architectural tools you need for production.
I love that. And to do that effectively, I think we need to establish a fundamental rule right up front. It's the core concept that makes the rest of this whole architecture make sense.
Okay, lay it on us.
To the container itself, it has absolutely no idea that it is a container.
Wait, so it's essentially trapped in like an existential illusion?
Precisely. I mean, it doesn't know it's a lightweight, nested, software-defined process running on a shared host. Because Docker leverages Linux network namespaces, the container looks around and just sees what any bare metal operating system sees.
Oh, wow. So it thinks it's completely alone.
Yeah. It sees a dedicated network interface, its own exclusive IP address, a default gateway, a routing table, its own DNS services. Yeah. All of that is meticulously constructed and fed to it by the Docker daemon.
So understanding how Docker builds that specific reality for the container is kind of the key to mastering everything else we're going to discuss today.
Exactly.
Okay, let's start at the absolute baseline then. What happens the very first time you install Docker on a Linux machine and you just run a container without specifying any network flags at all?
Well, it attaches to something called the default bridge network.
Right, but reading through the production guidelines from our sources, relying on that default bridge is actually a massive trap, isn't it?
It really is. I mean, the default bridge is kept around almost entirely for backward compatibility at this point. Yeah, it's perfectly fine if you're just, testing a single script locally, but it has severe technical shortcomings if you're trying to build a reliable multi-container system.
To kind of visualize why it's so problematic, I was thinking about it like this. Think of the default bridge network like a massive, chaotic, open plan office.
Oh, I like that analogy.
Right. Every single container you spin up without a specific network flag just gets shoved into this one giant room.
Yeah.
Unrelated applications, databases, cache layers, all mixed together.
Yeah, totally flat.
And worse, they don't know anyone's name. So they're forced to shout at each other using only their employee ID numbers, which in this case are IP addresses.
That is painfully accurate, and it really highlights the biggest missing feature. On the default bridge, there is no automatic DNS resolution between containers. Like you said, they can only communicate via those assigned IP addresses.
So if my web front end needs to talk to my backend API, I have to know the backend's exact IP address.
Yep.
But that IP address changes every single time the backend container restarts. Shouting employee IDs in a crowded room is just not a viable architecture.
Not at all. And what's fascinating here is how the explicit alternative fundamentally changes the rules of engagement, that alternative being the user-defined bridge network.
So when you explicitly create a custom network, even though it used the exact same underlying bridge driver as the default Docker, sort of upgrades the entire experience.
Exactly. You're basically moving them out of that chaotic open plan office and putting related services into isolated, soundproof conference rooms.
Oh, that makes so much sense. And I'm guessing the most critical upgrade in that soundproof room is the automatic DNS resolution.
You nailed it. If you attach a database container to a user-defined network and just name it DB, your web container can literally just send a request to the hostname DB.
And it just works.
It just works. Docker resolves the name instantly, routes the traffic perfectly, regardless of what dynamic IP address it assigned to the database that morning.
Now, I know some legacy tutorials out there still teach the -- link flag to get around the DNS issue on the default bridge. Like, you manually link the web container to the database container to share environment variables and stuff.
Oh man, if you see a tutorial recommending the link flag, just close the tab.
Really? That bad?
It is a deprecated legacy feature. It required you to manually create these static links, and if a container died, the links often broke. Modern best practices dictate using user-defined bridges for DNS.
Gotcha. So what about sharing configuration then?
For that, you use entirely different approaches now. If you need to share secrets or database credentials today, you inject them at runtime using a compose file, or mount a shared volume, or leverage Docker Swarm secrets.
Okay, here's where it gets really interesting.
Right.
Let's assume you've set up your user-defined bridge. Your containers are happily chatting with each other by name, completely isolated from the rest of the system. But they're entirely cut off from the outside world. So how does external traffic actually reach them? We have all typed -p8080:80 into our terminal. We know it maps the host's port 8080 to the container's port 80.
Sure.
But what is that command actually doing behind the scenes?
To understand that, we have to look at the Linux host's network stack. When you use the publish or -p flag, Docker isn't just spinning up a simple proxy process to listen for traffic. It's actively manipulating the host's kernel.
Wait, really? The kernel?
Yep. Specifically, it is installing network address translation or NAT rules directly into iptables.
So it's intercepting the traffic at the kernel level before it even reaches the standard routing processes.
Exactly. So a packet arrives at your host machine's physical network interface looking for port 8080. Before the host operating system can reject it or route it somewhere else, the iptable's pre-routing chain catches that packet. It rewrites the destination IP address from the host's public IP to the container's internal private IP address, changes the destination port to 80, and then just shoves it straight across the virtual bridge into the container's isolated network namespace.
That is incredibly efficient. But reading through the documentation, it highlights a crucial default behavior here that creates a massive security vulnerability if you aren't paying attention.
Yes. The default host binding address, this is a big one.
Right, because if you simply type -8080:80, you aren't specifying which of the host machine's network interfaces should actually accept this traffic.
And when you leave that blank, Docker defaults to binding that port to all available host IP addresses.
Meaning it binds to 0.0.0.0.
Precisely. Both IPv4 and IPv6 0.0.0.0.
Okay, so think about what that means. Imagine you are running a Redis cache on a cloud server that has a public IP address facing the internet. You spin up the Redis container and type -p6379:6379, thinking you're just opening it up so your local scripts on that machine can reach it. Yeah. Because of that 0.0.0.0.0 default, you have just exposed your unauthenticated Redis cache to the entire public internet.
And that is exactly how data breaches happen.
So how do you fix it? For the people listening, what's the actual command?
If we connect this to the bigger picture of production security, you must explicitly bind the port to the loopback address if you only want local access. So you type -p127.0.0.1:8080:80.
Oh, okay.
That specific command manipulates iptables to say, only intercept and route traffic that originates from inside this exact physical machine. All external traffic hitting port 8080 is just ignored.
That one modification is literally a career saver.
Absolutely.
Let's pivot back to the DNS magic we touched on earlier. We established that user-defined networks give us automatic name resolution. But how? Where is this DNS server actually running? Is it a process sitting on the Linux host somewhere?
This is actually one of the most elegant architectural choices Docker made. Custom networks use an embedded DNS server. Yeah, it isn't a separate container, and it isn't relying on your host's primary DNS daemon. It is a lightweight DNS resolver baked directly into the Docker daemon itself, and it gets injected into the container's network namespace at a very specific hard-coded IP address.
And that address is 127. 0.0.11, right?
That's the one.
So it's on the container's local loopback, but on the .11 address instead of the usual .1.
Correct. So whenever a container on a custom network tries to resolve a domain name, whether it's an internal container name DB or an external API like, say, api.stripe.com, the container's internal routing table directs that query straight to 127.0.11.
And then the Docker daemon intercepts it.
Exactly. The daemon catches that request. If you're looking for a local container, Docker checks its internal registry and hands back the private IP. If you're looking for Stripe's API, Docker seamlessly forwards that request out to whatever DNS servers are configured on the physical host machine.
Okay, for everyone listening, writing down that specific 127.0.21.1 IP address is a massive troubleshooting shortcut. The next time you shell into a production container and your curl command fails to resolve an external API, check the resolve.conf file inside the container.
Yes.
You will see name server 127.0.91 listed right there. If DNS is failing, you now know exactly which piece of the architecture is intercepting your traffic. It's not some mystery black box.
And it's also worth noting, as the documentation points out, there's actually no IPv6 equivalent for this specific resolver address.
Wait, really? What if I'm running an IPv6 network?
The IPv4 127.0.11 endpoint handles both A records for IPv4 and AAA records for IPv6. It works perfectly even if you're running an entirely IPv6-only container environment. It's like a universal constant in the Docker reality.
That's fascinating. Okay, so the bridge driver, whether default or user-defined, is clearly the standard workhorse.
Right.
But it fundamentally assumes all your containers are sitting on a single physical machine.
Right, which is rarely the case in real life.
Yep. Exactly. DevOps engineers rarely have the luxury of a single machine. We deal with legacy hardware integrations, high-frequency trading platforms, massive distributed swarms. When the bridge network isn't enough, what else is in Docker's networking toolkit?
Well, Docker designed the networking subsystem to be fully pluggable. There are several built-in drivers engineered for extremely specific architectural challenges.
Let's tackle the McVlan driver first. Because the best way I can describe McVlan is that it's like bypassing your corporate office's mailroom entirely and giving your individual desk its own direct street address.
I like that.
Basically, you're giving your container a fake mustache and a physical ID badge so it can pretend to be a literal piece of hardware sitting on the physical network rather than a nested virtual application.
That is a highly accurate way to visualize it. The McVlan driver bypasses the Docker host's bridge and port wrapping stack almost entirely.
So no iftables.
Nope. Instead, it assigns a unique, globally valid MAC address directly to the container's virtual network interface. And then it binds that virtual interface directly to the host's physical Ethernet adapter.
Wow.
Yeah, so to the physical network switch plugged into your server rack, that container doesn't look like a virtualized process hidden behind NAT. It looks indistinguishable from a physical server plugged into its own port.
Wait, I have to push back on this a little. If McVlan makes every single container look like a distinct physical device on the local network, doesn't that mean I have to manually manage IP allocations on my main corporate router for thousands of transient containers?
Yeah, it does.
Because if my DHCP server suddenly sees 1,000 new MASTI addresses appear in 10 seconds, that sounds like an absolute management nightmare.
You are entirely correct, and that is exactly why McVlan is not for general-purpose microservices. It requires meticulous IP address management on your broader network. You really only use McVlan to solve very specific legacy problems.
What kind of legacy problems?
Well, imagine you have an older application that monitors broadcast traffic on a subnet, or a proprietary licensing server that is hard-coded to expect a direct Layer 2 connection to a physical network without any routing or NAT in the way.
Oh, I've dealt with those.
Right. McVlan allows you to containerize that legacy application without having to rewrite its underlying networking logic.
That makes perfect sense. But what happens if you try that and your corporate network switch immediately kills the port? Because I've seen enterprise switches that have port security enabled. If they see 50 different MAC addresses coming from a single physical server port, they assume it's a MA spoofing attack and just shut the whole thing down.
And this raises an important question about network constraints, and it's precisely why Docker includes the IPFLAN driver.
Ah, IPFLAN.
Exactly.
Yeah.
IPFLAN operates very similarly to McVlan. It gives containers direct access to the physical network without BridgeNet, but with one critical difference.
It doesn't use unique MSS addresses.
Bingo. It does not assign unique MMAS addresses to the containers. All containers using IPLAN share the exact same MSE address as the host machine, but they receive their own distinct IP addresses.
Oh, nice. So bypasses those strict enterprise switch security rules entirely.
Precisely.
Okay, so MACFLAN and IPLAN solve our physical hardware integration problems. But what if my bottleneck isn't hardware compatibility, but raw network latency? Like, say I'm running a high-frequency load balancer or a massive reverse proxy, and the overhead of translating packets through Docker's virtual bridge and those IPTables rules is just slowing me down.
Then you reach for the host network driver.
The host driver.
Yeah. The host driver completely removes the network namespace isolation between the container and the host machine. The container does not get its own IP address. It doesn't use a virtual bridge at all. It literally just uses the host machine's networking stack directly.
So if my container runs a web server on port 80, it just binds directly to port 80 on the physical server. No -B flag required.
Exactly. You lose the security and flexibility of network isolation, but you entirely eliminate the performance overhead of network translation. The packets hit the physical network card and go straight into your application.
Incredible. Okay, that brings us to the opposite end of the spectrum. What if I don't care about a single machine's performance, but I have a cluster of 50 different host machines, and the containers spread across all of them need to act like they are sitting in the exact same room?
For multi-host distributed systems, you need the overlay network driver.
This is the swarm stuff, right?
Yes, this is the backbone of Docker Swarm. An overlay network literally creates a distributed, virtualized network on top of your existing host-specific networks.
How does it actually do that without requiring me to configure massive static routing tables on my corporate routers? That sounds like magic again.
It uses a technology called VXLAN, or Virtual Extensible LAN.
VXLAN.
Okay, when a container on host A wants to send a packet to a container on host B, the overlay driver intercepts that layer 2 network frame. It wraps that entire frame inside a standard layer 4 UDP packet.
Oh, wow. And then it fires that UDP packet across your standard physical network to host B. The Docker daemon on host B catches the UDP packet, unwraps the original frame, and delivers it to the destination container. It basically creates an invisible, secure tunnel between your machines.
So that's basically wrapping our container traffic in a standard UDP envelope and mailing it across the physical network, completely transparent to the underlying infrastructure.
That's a great way to put it.
That is brilliant. Okay, let's hit the last major driver, the non-network driver, which honestly at first glance sounds completely useless.
It sounds useless until you are audited for strict compliance requirements.
Ah, okay.
The NUN driver completely isolates the container at the network layer. It has no external internet access, no access to the host machine, and no access to other containers. It only has a local loopback interface.
So total L2 and L3 lockdown. Imagine you'd use that for a container that, say, takes in a file from a mounted volume, processes highly sensitive cryptographic keys or financial data, writes the result back to the volume, and then terminates. Exactly. Maximum security through digital air gapping. There is zero risk of it ever phoning home or leaking data over the network because the network simply does not exist.
So what does this all mean for the listener who is deploying complex architectures at scale? I mean, we have custom bridges, overlaid tunnels, McFarlane integrations, but what happens when you push these architectures to their absolute limits? I saw a scenario in the documentation that is just a classic DevOps headache.
Oh, let's explore it.
The documentation explicitly states a single container can be connected to multiple networks at the exact same time.
Yes.
So imagine I have a backend container. It is connected to a highly secure, isolated internal bridge network to talk to the database. But it's also connected to an external-facing bridge network to talk to an API gateway. It essentially has two virtual Ethernet interfaces.
Right.
If that container needs to send outbound traffic to some random public IP address on the internet, how does its internal routing table know which network to use as the exit door?
Well, if you do not explicitly configure it, Docker selects one of the networks dynamically to act as the default gateway.
Dynamically. That sounds dangerous.
It is. The problem is that dynamic selection is not guaranteed to be consistent. It can change every single time the container restarts.
Oh, no.
Yeah, leading to incredibly frustrating intermittent network failures where outbound traffic suddenly just drops into a black hole.
Intermittent routing failures. Literally the worst kind of 2 a.m. page. How do we make it deterministic?
Docker provides a configuration option called due priority, When you connect a container to a network, you can assign that specific connection a priority score. The default score is 0.
Okay.
If you configure the external-facing network connection to have a G priority of 1, Docker will permanently configure the container's internal routing table to route all unknown traffic, the 0.0.0.0/0 destination out, through that specific gateway.
Deterministic routing. That immediately solves the headache. Speaking of scaling limits, though, there's a hard limitation mentioned in the sources that someone listening is eventually going to hit. The 1,000 container limit.
Yes. This is a critical architectural warning straight from the official sources. If you connect 1,000 or more containers to a single bridge network, that network will become fundamentally unstable.
Really? Like, inter-container communication will just sporadically fail.
Yep.
Is that a bug in Docker's code base?
No, it's actually an inherent limitation in how the Linux kernel handles software bridges.
Interesting.
See, every time a container sends a packet, the kernel has to look up the destination MMATI address in its forwarding database, or FDB. It also relies heavily on ARP tables to map IPs to MC addresses.
Right.
When you dump thousands of virtual interfaces onto a single software bridge, the sheer volume of ARP broadcast traffic and the massive size of the forwarding database just overwhelm the kernel's event loop. It literally cannot process the routing updates fast enough.
So if you're migrating a massive legacy application and spinning up 2,000 microservice containers, you cannot just dump them all onto one user-defined bridge and call it a day.
No, you must segment them. You have to logically segment them across multiple networks.
And that logical segmentation brings up the final production reality we need to cover today: subnet exhaustion.
Oh, the silent killer of CI/CD pipelines.
Yes. Let's walk through exactly how this happens.
So imagine you have an automated GitHub Actions runner or a Jenkins server. Every time a developer pushes code, your pipeline spins up a brand new isolated Docker network, attaches a database and an app container, runs the integration tests, and then tears it down.
Sounds like standard DevOps best practice to me.
It is, until a pipeline crashes and fails to properly delete the network. Over time, you start accumulating orphan networks. The real problem lies in Docker's default subnet allocation. When you create a network without specifying an IP range, Docker automatically assigns it a massive subnet from its internal pool. Historically, Docker defaults to handing out /16 subnets. A single /16 block contains over 65,000 IP addresses.
That is an absurd amount of IPs for a test network that holds 2 containers.
Exactly. And because Docker's default address pool only covers a specific range, usually the 172.1min0 to 172.31.0.0 blocks, it can only hand out about 30 of these massive /16 subnets before it completely runs out of IP space.
Wow, only 30.
Yeah. Once that happens, your CI/CD pipeline tries to create the 31st network, Docker throws a subnet allocation error, and your entire deployment pipeline just grinds to a halt.
Furthermore, if Docker blindly grabs a subnet that your company's physical corporate VPN is already using, you create a catastrophic routing conflict. The host server won't know if a packet should go into the local Docker bridge or out over the VPN to the corporate office.
Exactly. It's a mess.
So how do we fix the allocation pool?
You take control of it in the Docker engine configuration file, the daemon.json. You can redefine the default address pools. Instead of letting Docker hand out /16 blocks, you configure it to hand out much smaller /24 blocks.
Okay, and a /24 subnet holds 256 IP addresses, right?
Right, which is more than enough for any single microservice stack or test environment.
And by doing that, you mathematically change the game. Instead of getting 30 networks out of your base address space, you can suddenly create thousands of distinct networks before ever risking exhaustion.
Exactly. It all comes back to proactive architecture. You cannot just rely on the magic abstraction.
Absolutely. Well, let's quickly recap the journey we've been on today. We started by identifying the trap of the legacy default bridge, moving our containers into isolated user-defined networks to unlock automatic DNS resolution.
Right, and we examined how port publishing physically manipulates IPTABL's NAT rules, and why leaving your host binding at 0.0.0.0 is an unacceptable security risk.
We tracked down the silent hero of Docker DNS, sitting inside the daemon at 127.0.0.1. We explored the networking multiverse, comparing the hardware integration of McCollVLAN with the VXLAN UDP tunneling of overlay networks.
And finally, we looked at real-world production constraints, managing gateway priorities for multi-network containers, respecting the kernel's 1,000 container limit, and properly slicing your subnet pools in daemon.json to prevent those pipeline failures.
Is a staggering amount of hidden complexity executing behind a very simple terminal command. But if we connect all of this back to the broader trajectory of our industry, it really highlights how profound software-defined networking has actually become.
It really does. And, it leaves me with a thought that I find endlessly fascinating.
Let's hear it.
If Docker can use a driver like McMuffin to make a lightweight, entirely software-defined process appear completely indistinguishable from a physical bare metal server to a corporate network switch, where does the physical network actually end and the software begin? Great. If every node, every router, and every server can be encapsulated and simulated so perfectly through tools like VXLAN and network namespaces that the hardware itself cannot tell the difference, could our entire global infrastructure eventually just become a nested Russian doll of virtual networks masquerading as hardware? I mean, are we even building physical networks anymore, or are we just laying down physical copper to run an endless, invisible labyrinth of software?
A nested Russian doll of virtual networks. It is a brilliant, slightly dizzying way to look at the infrastructure we build every day. Definitely something for you to ponder the next time you type Docker run and wait for the magic to happen. Thank you for joining us on this deep dive into the hidden reality of container networking. We will catch you on the next one.